Everyone. My name is Sophia. I'm an undergraduate student at Florida State University. My project is basically genomes for particle tracking. As I said, I'm an undergrad student. I'm in my junior year and I'm studying physics and astrophysics. So I'm just going to start with some background information. The Large Hadron Collider, as you know, accelerates protons and collides them. And then the compact muon solenoid CMAS detector is at one of the collision points. CMAS is a general purpose detector. So it is basically designed to observe any new physics phenomena that the LHC might reveal. Most of the particles produced in the collisions are unstable. They transform rapidly into stable particles that can be detected by the CMAS. And then by identifying these particles and measuring the momenta and energies, then piecing together all of the information, the detector can kind of recreate a picture of the collision for the analysis. Just more background information. How the CMAS works. So a powerful magnet is needed to bend charged particles. Bending the trajectories of the particle serves two purposes. One is identifying the charge of the particle, and the other is it allows us to measure the momentum of the particle. So high momentum particles bend less compared with low momentum ones. The tracking part, this is done by a silicon tracker. When a charged particle flies through the tracker layer, it interacts with the silicon and produces a hit. And then these hits can be joined together to identify the track. Measuring energy is very important for understanding what's happening at the collision point. This can be done with two calorimeters, the electromagnetic calorimeter and the hadron calorimeter. And then for the trigger part, since many interactions happen at the CMAS, events of interest are selected using a two-level trigger. The first level is basically the first round of selection. It uses only the muon systems and calorimeters for event reconstruction and does not receive tracking information. And the second level, the high level trigger, is able to receive information from all sub-detectors. It consists of a computing farm and has a few milliseconds for event processing. I'd like to talk about the high luminosity Large Hadron Colliders and some problems. The Large Hadron Collider will undergo an upgrade to increase the instantaneous luminosity after run 3. So the HL LHC will have 5 times more collisions per event. Occupancy of hits in the tracking system will increase proportionally. And with more luminosity. There's more pileup, basically. And traditional tracking algorithms, such as the Kalman filter, increase exponentially with pileup, and also time spent in tracking increases rapidly with pileup. So we might need other algorithms. Machine learning based algorithms for track reconstruction have been proposed, which scale linearly with pileup. So basically, the project summary, the goal is to use graph neural networks to reconstruct the trajectories of particles, because detector data can be represented as a graph with the hits, particles as nodes, and the possible trajectories as edges in the graph. The GNN is an interaction network that has 3 steps: graph building, finding the edge weights through edge classification, and building the track. My initial goal was to work on optimizing the GNN, and what I ended up doing was working on graph construction. And then basically the first steps were to understand the CMS data. I was working with the CT-bar no pileup sample. The data consisted of 2,200 events. And this is basically the distribution of hits in the detector. The graph can be a PyTorch, PyG data object. And that's how that's how I started with the graph building. And then after understanding graph buildings and the GNNs, I tried running the interaction network. There's 3 stages of the GNN are converting the checker data to hit graph, like I said, then predicting the edge weights, the probabilities of edges of real track segments, and then track building, cutting edge weights below some threshold, and applying a clustering algorithm. For the graph building part, they said the CMS event files become a hit graph, and one graph can be built from one event. Like you said, the graph can be a PyG data object, and the node information would be small r, not big R. The edge information would be dr, d capital R, dz, phi. The particle information is the particle ID, momentum, and eta. And the y label is 1 if true edge and it's true otherwise. I have here an example of the code I was working with in the beginning. So I started working with all possible pairs of hits. Then I calculated the phi, the z, dr, and then built segments joining the hits. And these are some of the graphs that I built. These are the RC plots. The black is for false edges, and then blue for check track segments. And then more on graph building is a group created a Python package. It can be pip installed. And the code is in this GitHub repository. The graph construction part should be configurable as a Python object, and then should make optimization easier. TrackML geometry is hard coded, so I had to adjust these parts that work for TrackML and make them work for the CMS data and the files, the events. And I started looking at the event plotter class, which is basically for building plots in Adafruit, RZ, and UV. And then I looked at the point cloud builder class, which is for point cloud construction and breaking up hits into sectors. And then the graph construction part would be extending the edges between these hits and the point clouds. These are some of the plots that I got working with the event plotter. The plots can be obtained from CMS event files. No need for building the graph first. There's not a lot of activity going on, but I was working with no pileup data. And then some things that I did and learned basically is I used CMS data to build the graphs and also ran the interaction network. I started studying graph building, and the first approach was building graphs by considering all pairs of hits and drawing an edge between them. The edge has certain geometric properties. Then I ended up working with point clouds. I could get the plots from the event plotter. And I also worked on adapting the point cloud builder to the CMS data until a certain point, because time constraint for coding experience prevented me from working more. But I would like to work more in this point clouds in the graph plotter class. So I would like to build graphs from the point clouds. And then I found out that the CMS data is more organized than TrackML data. It definitely improved my Python skills in learning the importance of making the code that's easy to be reused, repurposed. And that's it. Thank you very much. Thank you for listening to me. Thank you, IRIS-HEP. Thank you. I'd like to thank my mentor and then all of the members of our group, especially Gage, who was working with me all the time and answering my questions. And that's it. Thank you.
Thank you, Sophia. Any questions for Sophia? I didn't get a chance to before she began. Isabel, you were Sophia's mentor. Did you want to say a few words about Sophia's work?
Yeah, I think Sophia did a great job, especially considering that she's in Florida, or she was in Florida during some of this work. So, I think you made a lot of progress with Gage over the summer. So yeah, congratulations.
Thank you.
Let me introduce Manasvi. I was her mentor. So Manasvi Goel was our IRIS-HEP fellow, and Manasvi reads production and industrial engineering with minor in computer science at Delhi Technological University. She delivered an outstanding quality work this summer. Manasvi finished 2 C++ projects and wrote extensive documentation. First, she accelerated variable-sized array filling by implementing a global buffer. Second, she implemented a layout builder, a C++ template, a types-specialized nested array builder. And Manasvi will be presenting her work at ACAT this autumn. Take it away, Manasvi.
So, hi everyone. I am Manasvi, an undergraduate student from Delhi Technological University. This summer, I worked as an IRIS-HEP fellow under the mentorship of Jana Osborne and Jim Pivaski from Princeton University on the project titled Accelerating Awkward Array Builders. So, I'll start by giving a brief overview. Awkward Array is a scikit-HEP library for nested variable-size data, including arbitrary length lists, records, mixed types, and missing data, which is used to manipulate JSON-like data using NumPy-like idioms. Arrays are dynamically typed, but the operations on them are compiled and fast. Their behavior coincides with NumPy when the array dimensions are regular and generalizes when they are not. Awkward arrays are not only more concise, but they are much faster and use less memory than the Python equivalent expression. So this presentation represents the evolving view of best practices for creating awkward arrays in C++. Previously, the main code base was written in C++ with the idea that the downstream code would link to libawkward.so. But as Jim described in his talk at the last ACAT, that route is full of hidden gotchas. That's why the awkward tree manipulation needed to be re-implemented back into Python in order to make it more transparent to other Python libraries. We have now moved from C++ owning the data to Python owning the data. Awkward Array version 2 introduces a header-only C++ library that do not depend on any application binary interface. The method of a small header-only library that only fills array buffers for downstream code to pass from C++ to Python using the C types has considerably more promise. So my project aimed to accelerate the performance of layout builders used by the awkward array by preventing unnecessary memory copies, optimize allocation of memory, and improving the speeds by specifying the array builder type in advance. So initially the plan was just to modify the existing code of layout builder and global buffer in order to achieve the enhancement in performance, which included rewriting the layout builders in C++ from scratch. But as it turned out, the new global buffer and layout builder was going to be useful for another project by particle astrophysicist called CTA5, which has array types that are known at compile time. So the easiest way for them to get awkward arrays was to use a layout builder to fill the buffers and then send that to Python through PyBind 11. So in order to integrate it into their workflow, the layout builder needed to be a templated independent piece of C++ code, which is easily separable from the rest of the awkward C++ code base and implemented entirely in the header files. So the main tasks for my project were modifying the global buffer to use the multiple panels approach, to develop compile time templated header only C++ libraries, which can be dropped into any external project, and writing the unit test in C++, documentation, and also a user guide. So as we know that nowadays more front-end users use Python, but the large-scale processing still needs to have high performance. Therefore, we can combine Python and C++ in order to get advantage of the best features of both of the languages, so that we can have a Python user interface, but at the same time, take advantage of the performance and memory management of C++. So a mini package containing the layout builder, growable buffer, and the utilities now reside in a separate directory. The users can directly include it in their compilation rather than linking against any platform specific libraries. This new development makes the integration of awkward arrays into other projects easier and more portable. The code is minimal. It does not include all of the code needed to use awkward arrays in Python, nor does it have helper methods to pass through the bind 11 so that different projects can use different binding generators. The C++ users can use it to make arrays and then copy them to Python without any specialized data types, only the raw buffers, strings, and integers. The C++ code also simplifies the process of JIT compilation in root. Generating all the types via templates makes it easier to dynamically generate layout builder from strings in Python and then compiling it with Clang. This implementation also solves some of the drawbacks like packaging projects where native dependencies can be challenging. So the header only growable buffer, which uses the multiple panels approach, is already in use. But before talking about the new growable buffer, let's look at the previous implementation of growable buffer, which was a contiguous one-dimensional array that could grow indefinitely. And what were its shortcomings with the help of an illustrative example. So in this example, we have initially reserved 5 slots for the buffer with a resize factor of 1.5 and the following array of data to be added. Initially, the growable buffer constructor was called, which created an empty buffer with the reserved number of slots. The append function inserted one datum into the buffer and increased the length by 1, and this continued till the length was less than the reserved value. Once the length equal to the reserved value, reallocation was triggered by the set reserve function, which changed the value of reserved by multiplying it with the resize factor and taking the ceil value. So a new pointer was allocated with the size equal to the new reserve. A copy operation was performed, which copied the previously added element into the reallocated buffer, and the append operation was continued. Similarly, when the length was again equal to the reserved value, reallocation and copying are done, and the rest of the elements are added. So as we saw, in order to grow the buffer, the previous approach reallocated and copied the buffer every time it got filled so that the array remained contiguous. But as the size of the data increased, the performance reduced rapidly due to repeated reallocation and copying operations, which also created unnecessary memory copies. So in order to solve this problem, I modified the growable buffer to make it use the multiple panels approach. So in the new implementation of growable buffer, instead of reallocating and copying, I have used the multiple panels approach that are allocated as needed. That is when the growable buffer runs out of space. It is basically a singly linked list where a pointer points to the next panel. So taking the previous example, in this approach, the growable buffer constructor allocates an empty first panel with the reserved number of slots, which is also the head node of the linked list. PTR is a unique pointer to the panel data. The current PTR is a pointer that to the address of the first byte of the current panel. The data is appended one by one into the buffer till the length is less than reserved value, which was similar to the previous approach. But once this panel gets completely filled, instead of reallocating and copying, a new panel of the same size as the previous panel is allocated. The previous panel points to this new panel with the help of a next pointer. The current pointer becomes the pointer to this panel. The remaining data is now appended. Once this panel is also filled, another panel is allocated and the rest of the data is appended. So the last pointer points to the null. Uh, the panels are allocated with the smart pointers, so there are no memory leaks. So the reason why the multiple panels approach is a step up in performance is because that the global buffer is used to produce snapshots of the accumulated data by converting them into awkward arrays. So the external code copies the data out of the global buffer so that it can own it. And since we have to do a copy operation anyway, we can as well concatenate in the same operation. With concatenation being free, having no extra performance cost, we don't necessarily need the buffer to be contiguous, and we can let it be discontiguous as it grows to avoid more expensive ways of growing a buffer like reallocation and copy. So I have also written 10 C++ unit tests for different primitive data types to make sure that the methods in the new implementation were giving the expected results. These tests reside in a separate directory called test-cpp. Here I've shown the test for the complex data type on the left-hand side. In this test, the array elements are appended in the buffer using the multiple panels approach. An external pointer copies and concatenates the panels, and the result is checked against the expected output. It is the user's responsibility to allocate and deallocate in the data buffers. The other test demonstrates a method called extend, which is a new feature in the new global buffer. It gives an option to the user to add an entire array directly by taking the pointer and the size of the array instead of adding the data one by one iteratively. So in the earlier layout builder, which is now no longer in the main, we had a layout builder base class, but now we have a layout builder namespace with a set of templated static C++ classes implemented entirely in header files. The layout builder now uses growable buffer, so the growable buffer is also header only. There are three phases of using the layout builders. First is constructing the layout builders from the variadic template, and it is an implicit template instantiation. The second is filling the layout builders while repeatedly walking over the raw pointers, which is a pointer to the memory buffers managed by a smart pointer. And third is taking the data out of the user allocated buffers, and then the user can pass them to Python if they want. And it is also a one-time copy now. So the layout builder provides information about the following. First is what's the awkward form, which is basically a unique description of the awkward array and returns a JSON-like string and its form keys. What are the names, size, and the name of the buffers? For this, we map the node names to the number of bytes of the nodes. At this point, the buffer is still a sequence of panels. This is an internal implementation detail to extract the data because we already have the AK from buffers function. And third is what data is filled in the buffers from the key form key node and the user given pointer. We fill the data into this pointer. When the layout builder is filling the user own buffer, it does concatenation while copying. The user can pass this information over the border from C++ to Python using PyBand 11. So let's take an example of one of the most interesting layout builders, which is the record layout builder. So an array of events of one value per event attributes and different length lists of particles can be modeled using only records and variable length lists. This is what the user code looks like for building that with the layout builder. So here we have a record layout builder with the fields NumPy layout builder and the offset layout builder. The builder content is a heterogeneous type tuple. The field names are non-type template parameters which are defined by the user. Note that we cannot template on string because this feature only comes from C++20. That is why a user has to provide a map for passing the field names of parameters to the record layout builder. And to do any operation on the tuple, we use the lambda function. On the right hand side, we can see how the users can add the data to the builders to make the records. Here we have created 3 records, and the resultant array would look something like this, which is demonstrated here. The user has the option to check the validity of the buffer via the isValid method in order to make sure that there are no errors while filling the data. The user can call it on every entry if they want. If they want to trade safety for speed, they can also retrieve the information needed to allocate the empty buffers as a map of their names to the size in bytes, and allocate the buffers using the user given pointer and the same names and sizes as the previous step, and fill the data in the pointers. Here we can see the form for the record layout builder, which is generated by the layout builder, which consists of details like the class name, contents, primitive type, and the form key. And since this is the case for record layout builder, we also have the fields and their contents too. So along the way, we realized that there were some subtle issues, such as dealing with records that have no fields. So different builders were needed for records with the named fields like records, and the records with whose fields were not named, like the tuple. So besides the record layout builder that created record with fields, we created 2 additional layout builders. First was the tuple layout builder, which created records with no field names, like in the example shown here. And the other was the empty layout builder, which created empty records by taking a Boolean parameter is tuple and return the first form if it is not a tuple, and the second form given here if in case it was a tuple. So there are in total 14 classes in the layout builder namespace. Every class is templated, and any other layout builder can be its template parameters. So these are sufficient to build every awkward array that we have. So now both the layout builders and the array builders have a similar interface for concatenating the buffers by using their respective 2 buffers method. Both also use the new growable buffer with the multiple panels. The layout builder concatenates the data and fills it in a map of form keys and the user defined pointers, whereas the array builder also returns the form and casts the type, for example, from int64 to float64 besides the concatenation. In the version 1, the array builder was based on the shared pointer, which was shared with Python. In the version 2, we moved from Python owning the data, that is a copy of unique pointer data in C++ to a NumPy allocated array, which was the case until a while ago. But now the Python binding invokes the array builder 2 buffers method. So the only full copy of the data is owned by Python. Awkward arrays to our data frame and from our data frame are now using the new layout builder. So this is an example how it is being used in the R data frame. Using the header only C++ library, it simplifies the process of JIT compilation using CPPYY. So some of the key insights are the minimum requirement for the layout builder is C++14, as we use generalized lambda expressions, which allow us to deduce the type of parameters during the compile time. The C++ tests are configured to be built using CMake list hist.txt. They are not run with the local build because we have restricted the code to work on a minimum C++14, so they won't run on Ubuntu, which requires C++11. The memory management, so the unique pointer owns and manages the memory of the multiple panels. So we don't need to worry about managing the memory in global buffer. Earlier, we needed a copy of a unique pointer data in C++ to a NumPy allocated array. But since the array builder is now using the new global buffer, now there isn't even a single unique pointer anymore. The only full copy of the data is allocated and owned by NumPy. The memory management for data created by array builders has dramatically changed in the last few versions, with more and more reliance on NumPy owning the data. So in addition to the above, I also wrote some documentation for the layout builder and global buffer so that the user can get the documentation along with the code, which looks something like this. And I also prepared a user guide that can guide the users on how to integrate awkward arrays via layout builders into their projects and help in expanding the scope of awkward arrays beyond the HEP community. Also, this project is selected for an oral presentation titled The Awkward World of Python and C++ at this year's ACAT workshop, which will be held in Italy at the last week of this month. So this summer has been a great learning experience for me, and I would like to thank Peter, my mentors Yana and Jim, for giving me this opportunity and their constant support, and the entire IRIS-HEP community for this rewarding journey. Thank you very much. You can ask if you have any questions.
Thank you, Manasvi. We have one question in the chat from Gordon. Do you want me to read it, Gordon, or you just want to ask the question?
Can you please?
I'll read it.
Yeah.
Gordon asked, is the data recopied from the panels, or do the kernels now operate on the panels? Sorry, untrained, lots of noise. It's in the chat if you want to see it too.
So basically, we use the global, like we just use the panels to grow the buffers that we have. So like nothing much has changed as respect to like that operate on the panel. Like the panels are just for growing the buffers. I don't think it has any other significance in the project. We just are using it to grow the buffers that we have so that we don't have to do the reallocation and copying again and again.
Okay, great. Gordon says very nice. So any other questions? Henry, you want to say a few words about Aman's work?
Yep. So Aman was with us last year. Did work on Hist. You might know him from last year. This year he did work on Upright Browser, continued work on Hist, and just generally did quite a bit with training, and was involved in the HSF, and was involved in lots of different areas. Okay, Aman, go ahead.
All right, thank you. Hi, everyone. So today I'll present the Hist Serialization and Interactivity project as a part of the IRIS-HEP Fellowship. So I was mentored by Henry from Princeton University. A little about me. I'm a recent graduate in computer science and mathematics from the University of Delhi. I was the IRIS-HEP Fellow last year, as Henry mentioned, and this year I continued working on Hist and Upright Browser. Then I've been a member of the HSF training working group, where I've been involved in different capacities. and I'm interested in everything research software engineering. And in fact, right now I'm looking to get into a full-time research software engineering role. So I worked with the Analyst Systems Working Group at IRIS-HEP, and this is the scope of analysis systems. And I worked somewhere here along with Boost Histogram and Hist. And we also had Approved Browser, which is more of a library which allows us to view data files. So first, we'll talk about the Hist library. Now, Hist is a powerful histogramming tool for analysis based on Boost Histogram. So Hist is basically a front-end library which adds on features to Boost Histogram. And we can use plotting tools, shortcuts, and we have a lot of new ideas in Hist which were not there present in Boost Histogram. So the latest release for Hist was 2.6.2, which includes a lot of features and improvements. So this is how we represent a histogram in Hist. Now, the graphical representation of a group frequency distribution with continuous classes is called a histogram. That is the technical definition. Now, when we define a histogram as an object, we treat it as a collection of access objects and storage that allows us to perform multiple operations on the object itself and to play around with it and to carry out different operations. Now, I was able to extend the documentation for Hist, wherein now the documentation that we have is almost similar to Boost Histogram. Now we have all the sections that are analogous to Boost Histogram in Hist 2. And I mean, the ultimate goal is to have a unified documentation, but right now we have almost a similar documentation where we have different sections, such as say subclassing and NumPy compatibility and everything on the Hist syntax rather than the Boost Histogram. Then Hist now also has binder support. I think Matthew helped us add that support, and with the binder, it basically gives us one-click capability of sharing interactive and reproducible environments. Then some miscellaneous features that I was able to work on. So Hist now has the SciPy dependency as optional, and we're able to avoid those costs which are required to install SciPy every time. Then there was a seg fault that was caused by the empty access and the kernel used to crash, which has been fixed now. The Hist library now fallbacks on the normal rep if the histogram object is too large. And the Hist library now allows overwriting the labels for the plot. And Hist also now supports two new Nox sessions, regenerate and pilot. And Nox is basically a task runner which helps us in quick development and in running tasks and tests quickly. So now I'll talk about the Uproot browser, which was majority of the work where I did. Now, Uproot browser is a Plotex-based command line library in which the command line interface is provided by Click, which is another Python library. And we use Click to basically interface with the command line via commands. Say we're giving a flag or we're giving a file or a path over the command line itself. That is all operated by Click. And it is powered by Hist in the background, where it uses Hist to interact with the histogram objects. And the TUI is put together by Textual. Now, its aim is to enable a user to browse and look inside a root file completely via the terminal. It takes its inspiration from the root object browser. Some of you might be familiar with it if you have used the root library and the browser. So the need for Uproot browser arose when we had the root object browser. Basically, is a part of the complete root framework, which is a large framework, and it requires a GUI and a web browser to function. So the Uproot browser, where it fits in there, is it offers something that is an alternative, which is high performance, lightweight, efficient, and is also accessible via universal user interface. So since we do not require a GUI or a web browser interface to interact with the browser itself and can work within the terminal, we reduce a lot of accessibility need there. So this is the root browser originally from the root library, and we'll see how similar the Uproot browser is to this. So Uproot browser currently provides the following features. We can use the browse command, which can be used to display the TUI, that is the terminal user interface. And that basically gives us an interactive window within the terminal. Then we can use the plot command, which can be used to display a plot on the terminal itself that uses flow text to render the plot. Then we can use the tree command to display the tree of all the contents of the root file. And if if a Mac OS user is using item, you can also have plots on item using the flag here. Now, this is the tree command, which gives basically the tree view of a root file and shows all the objects inside for easy navigation. So it also gives all the metadata about the object, such as its signature, type, and value count. So here you can see how we have different histograms and different objects within the root file. Then we have a TUI, that is terminal user interface, which ties everything together. So the browse command can be used to bring up the TUI, and it deploys a terminal application which can be navigated via mouse or keyboard. It combines the tree and the plot functionality and has various modes and features. It can be controlled via key bindings too, which is basically right now the standard keys that we use, up, down, left, right arrows. And it interfaces via click and textual and uses flow text and Hist in the backend. So I'll show a little demo of Upload Browser here. Now, as we can see, this is the complete window that we have. Now, on the left, we have the tree where it is interactive, where you can scroll through the tree and look at the different objects there. And here we see that the errors are rendered in rich. Now, if you click on, say, a histogram object, we see the plot on the right, which is rendered by flow text. And we can also switch the sidebar to have the full screen object view. Then the interactivity also can be worked via the keyboard, as I said. And then there is also styling available via the hover command. So when you hover, you can see there are different underlines, there are different interfaces that you're able to see. Then other than that, just a second. Yeah. So other than that, right now the approved browser is waiting for textual's release of the CSS version. So the TUI is based on textual, which is porting to CSS, and beyond which we'll also like to port approved browser to CSS too. So some miscellaneous features that we added in approved browser, you can get the whole you can get the code which you use to generate the plot or the figure, and you dump it on the terminal on quit. Then we've added tests for tree views. Then the browse command was added where everything is basically tied together. Then we re-implemented the header specifically for Approved Browser and added better plot information. So that was about Approved Browser. I was also able to work with the HSEP training working group as a part of community interactions. So I helped in the development of matplotlib for HEP module under the HSEP training working group. And that was done as a part of education and outreach efforts. I was an instructor at the matplotlib training held in April, which aimed to inculcate computational and analysis skills in students. I was also a mentor at the Software Cup entry in March, and very recently in September too, in fact, where we sort of help students whenever they're stuck with Bash, Git, Python, and Root, and the different tools that are being used in the workshop itself. And I was also the instructor for Scikit-HEP and Uproot at the July workshop for Software Cup entry. I was also able to present my work at a few workshops and conferences. So I gave the boost histogram in his talk along with Henry in March at the topical meeting, at the PyHEP working group topical meeting. Then very recently, I was able to deliver the talk Histograms as Objects, a tool for efficient analysis and interactive with J at PyHEP. And that was where we went over the boost histogram Hist and Approved Browser ecosystem. And then I was also able to present HSEP training. And there we presented teaching Python the sustainable way, lessons learned at HSEP training. So where we presented how we got to develop all the modules there and how the working group functions. I would like to acknowledge and extend my sincere gratitude to Henry, who has guided me throughout the project. And he has helped me in understanding important concept and answered all my queries and doubts. and it has been a wonderful experience to have him as my mentor. I would also like to thank Peter and the Princeton Computing Group for their valuable feedback and support. And finally, I'm really grateful to the whole IRIS-HEP community for being warm, welcoming, and supportive throughout the fellowship. Thank you.
Oh, thank you, Aman. A very nice talk. Any questions for Aman?
Yeah, can I ask a quick question? Hopefully my audio is now good enough to hear.
Yeah, you're good.
Okay, so that's a great talk, a lot of work, and I apologize because I'm on a phone, so I can't always see everything that you had up there. But when you're going through Uproot browser, you mentioned very quickly that errors were rendered in rich, but I couldn't see what kind of objects were causing the errors. What is I guess this is, you know, the spot where Uproot and Awkward don't support what's in the
Yeah.
in the file.
So right now, the Uproot browser supports a handful of objects.
What sorts of things generate those errors? Yeah.
Yeah. So all the unknown objects right now are rendered as a rich error. So earlier it used to crash altogether when it when it saw anything it didn't recognize. So right now, say if we're able to recognize a th1f, other than that, everything else would be presented as an error. And the unknowns.
Okay. So all right. So th1f is the current limitation of support.
Yeah, there are like trees are also supported, T trees are also supported. And I mean, it's been developed in a way where we add support rather than having support for everything at once. So everything is first directed to an error and then we add support to it.
No, that totally makes sense. All right, thanks. Really nice work.
Thank you.
Some things like a 3D histogram, I'm not totally sure what we should plot in a terminal. So.
Okay. Henry or Jim, do you want to say anything about Saransh's work?
Well, I wasn't really prepared to, but this was and I guess he'll be talking about what exactly he did, but the state of things when he started was vector was in kind of like that 90% level, almost there, but it's the last 10% that's always the difficult part, involving a lot of work and thought in order to make it into a really usable library, and then that's what Saransh did.
Hi everyone, I am Saransh, an undergraduate at University of Delhi, and this summer I worked under Henry and Jim on Vector, which is a scikit-HEP package closely related with Awkward and the analysis systems group. The main goals of this project was to work on Vector's constructors, documentations, and benchmarks, which I will be discussing more about in the upcoming slides. So a quick introduction to Vector. Vector allows working with 2D, 3D, and Lorentz vectors to solve common physics like physics problems in a NumPy-like way. So, and Vector is not only limited to HEP. So you can use Vector in any mathematical scenario, but a Vector was created with keeping HEP in mind. Vector uses names and conventions set by roots T Lorentz vector and the Lorentz vector under math namespace. Also HEP vector under Henry's account, which was the starting point for Vector, and Coffee.nanoevents.methods.vector. Users can create Vector in a variety of coordinate systems, including Cartesian, cylindrical, spherical, and any combination of these with time or proper time for Lorentz vectors. Vector seamlessly integrates with the existing scikit-HEP libraries, especially with Awkward. So you can create vectors directly from Awkward using the with name argument, or you can also create vectors using the vector library. And Vector comes loaded with 3+2 backends, which are a pure Python object backend, a NumPy backend, an Awkward array backend, an object number backend, and Awkward number backend. The number backends leverages just 10 times compilation to perform quick calculations on vectors, especially if you have like a huge list of vectors. Going through a basic user example of vectors. So this is using the object backend. You can construct vectors using the OBJ constructor, and this is the one that is using my work. I will also be showing up examples which were before the fellowship period. So you can construct a normal object type vector using vector.obj, pass in the coordinates with the names, and that's it. It would create a normal vector for you, and you can perform any mathematical calculation on that vector, not limited to HEP. So you can add those two vectors. You can also convert that vector to vector 3D, 3D type vector, or change the coordinate types. So going from x and y to rho phi eta tau, rho phi eta t, and eta and t would automatically assume to be 0. Then you can perform vector operations like the dot product, the cross products, and take out the azimuthal values or the longitudinal values, rotate the z value, scale the vector, check if the vector is perpendicular to any existing vector, and anything that you would want to do with a normal vector. Then the vector, as it was developed for HEP, so you can create awkward arrays of vectors. So in this particular example, I take in data from scikit-dep test data and put it all into vector.zip, which constructs a momentum array 4D vector, which is basically a list of vector with variable length, and you can perform the same calculations on this particular array which you were performing on a single vector that was an object type vector. So you can scale it, you can gather the azimuthal coordinates, or you can gather the px coordinates because it was a momentum type vector. Detailed user examples for vector is available in vectors readme, vectors documentation, and there's also a PyHep talk that I gave I think a month back, which also has a detailed user example for vector. So you can check them out if you're interested in vector. And this is how a vector is architectured inside the code base. So everything is, the vectors code base is very scalable. So this whole chart is for a particular backend, which is object. So you can replace object with, say, numpy or awkward, and you would get a similar chart. Awkward would additionally have vector array classes, which directly inherit from awkward array. And so this makes everything more scalable. You can add more backends without worrying about adding redundant code. Now moving on to my project, the goals were constructors, exposing inner constructors and classes to the user API, documentation, improving the API documentation, adding tutorials and adding documentation for the new features, and benchmarks. So developing a benchmark suite for vector, which could then be propagated to other scikit-dep packages. So summarizing, preparing vector for its first major release. Moving on to motivation for each of these goals, and then I'll be discussing whether these goals were met and at what point is vector right now. So the motivation for constructor was that the user-facing API of vector was not exposing its the true API, which are the Python classes. Rather, vector provided wrapper functions named as obj, arr, and awk, which we discussed in the examples before to users. And the wrapper method of these classes also displayed these same wrapper functions, so which made the constructors even more confusing or ambiguous to vectors users. This is how the object type constructors looked before my fellowship period. So if you would construct a vector if you would call vector.obj, the wrapper that it would show would be exactly the same as you were inputting, except for the momentum type vector. So in the third cell, you would see I am providing px and y. So vector would automatically recognize that I am trying to construct a momentum vector, and it would automatically print px and py. This particular wrapper is not very user-friendly and informative, so I don't know what type of vector is constructed. I could infer what type of vector is constructed through the argument that are printed, but it was not very user-friendly. Additionally, you could create vectors from class methods, so such as from xy, from row phi. Every coordinate, every possible coordinate combination had its particular class method, and they would also use a similar wrapper, so vector.obj, and then showing in the coordinates. And you could not create a vector with the normal vector object classes. So, for example, if I pass in 1, 2 in vector object 2D, it throws an error. And let's say if I pass in x equals to 1 and y equals to 2 in vector object 2D, it would again pass an error. Also, you could have passed, I have not shown it here, but you could have passed anything in place of 1, 2. So for example, you could have passed a complex number, or let's say a Boolean value instead of integer or floating point numbers, which vector would not complain at the constructor level for those values. But when you go down the code and perform a mathematical operation, vector would complain that, and then you would have to correct the original constructors to make your script work. This is how the object type constructors look now. So if you're using a PI release, or if you're installing vector from pip, you would not see these constructors right now, as these are still available in a feature branch. So if you would install that particular feature branch, then you would be seeing these constructors. And we're trying to get those feature branches merged and get the major release of vector out. So if now you pass, let's say, if now you call vector.obj with x equals to 1 and y equals to 2, you would clearly see what type of vector you're constructing, which is a vector object 2D. Similarly for the momentum vectors, and similarly for the class methods that you would be using. Additionally, you can also pass in the coordinate names and the coordinate values directly into vector object classes, or any vector classes. So the dunder init method now works as it should have before. So that was a quality of life improvement inside a vector. Moving on to NumPy type constructor. So as I discussed, vector right now has 3 backends, 3 non-number backends, which are object type, NumPy type, and awkward type, and I worked on all of them. So before the fellowship period, you could have constructed NumPy type vector using vector.array with a small a. And as per documentation, you could have also constructed NumPy type vectors using vector.arr with a small a, but surprisingly, it constructed awkward type vectors. So that was a bug inside vector. You could have also passed in weird values. So for example, here I am passing in a complex value and labeling it as, I'm passing in a Boolean type value and labeling it as a complex value, and vector is not complaining at all. So, but if I go down the road and perform a vector calculation on it, it would complain at that point. This is how the NumPy constructors look now after the fellowship period, and this has been merged inside vector v0.9. So if you're using vector from pip, you should be able to use everything written here. The array constructors work as it is. The ARR constructor now constructs NumPy vector as it should have, and the constructors now complain if you are passing in a data type that they don't identify, or that vectors are not supposed to have. Plus, you can also construct vector using vector NumPy 2D or vector NumPy XD classes, similar to that you were constructing with vector object classes. Moving on to the awkward constructors, and here I'm taking the example from the slides before. So using escape test data to load uproot HZZ file, and then taking in, reading the tree, taking in the branches, which are essentially awkward arrays. So this also shows how vector integrates with the existing scikit-hep packages. So for example, escape test data uproot, and though I'm not importing awkward directly here, but these variables px, py, pz, and e are essentially awkward arrays. So you can pass in these inside vector.awk or awk. So if, okay, this was before the fellowship period. So at this point, vector would automatically construct a vector, which is something that is wrong. So here a user wanted to construct a list of vector with each list having a variable length, but here it constructs 2421 momentum type vectors, which is not what a user wanted. And obviously a vector cannot have coordinate values as a list. So this was again a type checking bug inside vector. And you could have also done, for example, pass in a complex type and a Boolean type inside a vector, and it would not complete at the constructor level. Also, the backends module was made public in vector v0.9, and all of the wrappers inside the backend module are also the default wrappers that Python provided. So that was something that could have been worked on. This is how the awkward type constructors look now. I hope this is visible. So if I pass the same values inside vector.awk now, it throws an error that the coordinate must be of type int or float, but I can do the same with vector.zip, which essentially uses ak.zip inside. So it's basically vector.awk and then calling ak.zip with the coordinates inside. And it constructs the vector that we wanted, a list, variable length lists of vector. It also rejects complex types and any coordinate types that are not, that a user would not like to use through using vector. And obviously it has better wrappers. So now that the backend module is public, it does not use the default Python wrappers, rather it uses better wrappers. Moving on to the documentation. So the motivation for documentation was that vector lacked proper user as well as API documentation and tutorials. So if you were using vector as a developer, then you could have gone through the documentation and understood what how the API documentation and tutorials were structured. But if you were a beginner and very new to vector, then the documentation was not so good. And there were not detailed explanations in tutorials, and most of the functions and classes did not contain docstrings. So this was the documentation before the fellowship period. The API reference was not structured well, plus it had no information about vector, rather just pointing to API reference and examples. This is how the documentation looks right now. You can visit it on vector.readthedocs.io. So it has a better structure for API reference, more docstrings for classes, public classes and public functions, a better structured example gallery, and a better structured overview page. So now we also have talks about vector and getting help, everything a beginner would need to get started with vector. The last goal was benchmarks, and motivation for this was that scikit-hep packages including vector lack benchmarks. So benchmarks, benchmarking Python library is something that is picking up right now because of that a lot of libraries are picking up right now because of ASV or airspeed velocity, and that is what we are planning to use for vector. Benchmarking would be a valuable addition to vector project, which could then be propagated to other scikit-hep packages in the future. The benchmarking suite is not yet visible on GitHub, but this is a minimal benchmarking suite that I have running locally. So here I am taking in three things. So right now I'm checking the memory of creating what is the memory that is used while creating an awkward vector, which is the mem_awkward_creation, then timing a creation of awkward vector, and then timing a creation of numpy vector. So this is from vector v0.8.5 to vector v0.10.0, and I will be populating it with the course of time. If I zoom in to a particular benchmark, so for example, the time_numpy_creation, this is how it looks like with evenly spaced commits and with the tags here intact. So you can see there was only a one commit between v0.9.0 and v0.10.0. Additionally, we can see a large regression here. So at this particular commit, there was ASV is telling us that at this particular commit, some code was added that slowed down the creation of numpy type vectors. So in an ideal world, this would be reported in a pull request. So for example, you create a pull request and that slows down a specific functionality of vector, it would be reported then and there, and a particular, let's say a GitHub action would fail, telling the maintainer that this pull request is slowing down something. If I look at the regressions at presented by ASV, we can see that there is a regression at this commit, and I went through the GitHub commit logs and saw that the hash of that particular commit matched with this commit. So this is the commit where me and Jim added type checks into constructors. So this is where now the constructors check the metadata of the NumPy structured array provided through vector constructors to make sure that users are not providing data types like complex numbers or Boolean numbers. And I think we were okay with vector taking this particular time hit because this was something that was required. Okay, moving on to work done outside of vector. Okay. Okay, I think I cannot load the chat, but there were some comments here. Okay, I'll wrap it up quickly. Moving on to work done outside vector. So there is a new build backend for vector. So hatch that requires no setup.py file and not for installation or not for editable installations. We now have type safety. All constructors are type safe. There are a lot of CI development. So adding Python 3.10 and 3.11 dev support, removing 3.6 support, and so on. We also have awkward.v_v2 support. So vector does not currently run on awkward v2, but it is tested on awkward v2. So it won't completely break down once awkward v2 is out. And then a lot of miscellaneous fixes and additions. So static typing fixes, constructor bugs, and repo review. Work done outside of vectors. This was related to my fellowship work, but done outside of vector. So a minor bug fix in awkward, adding support for coverage in cookie, adding a new page on coverage on scikit-hep.github.io, which is live right now. So you can check that out. And some fixes in Hist and migrating HEP tutorials to use vector from plain Python. So promoting vector in a sense and letting people know that vector is ready to be used inside of your HEP workflows. The final outcomes with regard to this project was that vector v0.9 and v0.10 are out. So you can check them out on GitHub and PyPI. These are some of the features and bug fixes and documentation fixes that they introduced. And we are planning on releasing vector v 1.0.0, a major release with the constructors. What's next after the fellowship period has ended? So developing awkward constructors. I still haven't worked on direct awkward constructors, and then a solid support for awkward v2. So awkward v2 is scheduled in December, and we're planning on supporting vector with awkward v2 and v1 both. Then a major release, which is v1.0.0, setting up infrastructure and website for benchmarks on GitHub, and then probably propagating those benchmarks to other scikit-hep packages, and then at last maintaining the vector and keeping it up to date with the scikit-hep packages. These were some of the talks that I gave, and which one of them is upcoming poster at ACAT 2022 and a talk at PyHep with Henry and Jim about vector. Then I also participated as vectors maintainer at the PyHep Hacker Shop and engaged in a lot of discussions with scikit-hep developers. Yeah, thank you. I had a wonderful time contributing to the scikit-hep ecosystem, and I would especially like to thank my mentors, Henry and Jim, and members of IRIS-HEP, Princeton Computing, and scikit-hep. I would take up any questions if there are any.
Thank you, Saransh. Any questions for Saransh? Matthew, you have your hand raised?
Yeah. First, thanks for the really nice talk and also for the excellent project work. So one of the things that you showed in your talk is that you're using airspeed velocity to do the performance benchmarking, which I think is super cool and a really great tool. The question that I had is, when you were doing the actual benchmarking, were you doing this in CI with GitHub Actions, or were you doing this on a local machine? The reason I ask is because at SciPy 2022, when I was having some discussions with the maintainer of the PolyAstro package who uses airspeed velocity, he was commenting on how trying to do performance benchmarking without having dedicated hardware infrastructure can be really challenging because using GitHub Actions can add quite a bit of noise.
Right now I was doing it on my local machine, but there are some projects that I'm associated with that use GitHub Actions as a primary a machine for ASV. And I don't think I know a project that uses some dedicated setup for running benchmarks.
Okay, cool. Yeah, my assumption was that you were just using your local machine, but I was curious. Yeah, I might have some follow-up questions later on, but thanks.
No worries. I'll drop in the projects in the chat.
Okay. Any other questions for Saransh?
I'm Zoe Bilodeau. I've been working on fast integration of Poisson distributions with the Xenon Dark Matter project. I'm a senior computer science major at Skidmore College, and my mentors on this project were Tina Peters from the University of Delaware and Chris Tunnell with Rice University. So the Xenon Dark Matter project is currently on its 4th version, Xenon NT, and the goal of this project is to detect dark matter using a dual phase time projection chamber filled with liquid and gaseous xenon. So space particles float through the detector and react with the xenon in a way that emits light, and the light is tracked by sensors on the top and bottom of the tank in a way that should be unique enough that we can identify it as dark matter. Here's a picture of the last version of the experiment. It's located deep in a lab and deep in a mountain in Gran Sasso, Italy, to filter out other particles that could interfere with the experiment. So my project and goals was to write a program that can quickly calculate correlations between sensors concerning the number of electrons the sensors are detecting and the sensors' positions relative to each other in the tank. And these correlations should allow us to improve the accuracy of positional reconstruction and help us fill in gaps of information left by broken sensors. So going further into positional reconstruction, so when a particle flies in and interacts with the xenon, one of them ionizes and produces light, as I explained. We are tracking the amount of light produced, but we need to know where horizontally in the tank the interaction occurred based on the patterns of light produced. And we need to know this because if the interaction occurs close to the walls of the tank, decay from the metal that makes up the sides of the tank could react with the xenon and create invalid data. And we want to make sure we know that that's not happening. Bayesian networks are what we're using to do positional reconstruction. A Bayesian network is a probabilistic graphical model that models conditional dependencies. So right now, our Bayesian network implies that the number of electrons a sensor is detecting is dependent on interaction position in the tank and the number of electrons emitted from the interaction, which is true, but there are edges missing between the sensors. And this implies that the number of electrons sensors detect is not, there's no relationship between that, but we know that's not true based on their position, because if two sensors are next to each other, they're likely to have detected a similar number of electrons, especially compared to sensors very far away from each other. And so we'd like to quantify that relationship using positional reconstruction and also to fill in gaps of information left by broken sensors. So sensors are very sensitive and break non-infrequently and are super difficult to fix as you have to open the tank, which we don't want to do. So we want to be able to quantify these relationships between sensors so we can effectively guess what number of electrons broken sensors most likely would have detected. So to do this, we first create a giant probability distribution, which we'll eventually be integrating over. The type of distribution we're creating is a Poisson distribution. As electrons are discrete, you can't have half an electron. And so we're using the Poisson probability mass function, which is in the bottom right corner. We're doing this in groups of 7 sensors so that it won't get too large. And there's one probability distribution for each Birkin sensor. And to create the probability distribution, we calculate a sensor's mu value based on radial position, and we calculate a mu value for each possible interaction position that could have been predicted. So for each Birkin sensor, we'll have a number of different predictions based on different mu values, which are based on different possible interaction positions. So problems we ran into with some PMF, we have to alter the way we're calculating this slightly because there's factorial in the denominator, and our x values can go over 400 or around 400, but as the computer can only handle x values up to around 170, so we had to compute the log PMF using the log factorial. And as we can't just compute the factorial and then take the log, we had to find a log factorial approximation. So we looked at a number of different log factorial approximation and log gamma functions, but we settled on the Ramanujan log factorial approximation as it's very accurate, it scales well, and avoids the problem we were having. This ended up being helpful as we can use the log PMF to add probabilities together instead of multiplying them together, because we're supposed to be multiplying them, and this prevents underflow. Here's a visualization of a giant Poisson distribution with 2 Birkin sensors, and this is only at 1 interaction position, so it's easy to look at. To create the giant probability distribution, we essentially multiply all combinations of probabilities in the distributions together. In the future, we might use the Poisson bivariate function instead, but right now we're just multiplying. And you can see at the mu value is mu value for each Birkin sensor is where it most likely, it's the number of electrons it most likely detected. It's 12 and 7. And the probability is highest. So the next step in this computation is integrating. So we want to integrate over all possible values the sensor could have had. This involves creating the giant Poisson distribution in a large array and adding a dimension position. So all the different PMFs we're calculating for different interaction positions are matched up in the array. So we know what interaction position we're calculating for. And these arrays can get very large. So we have to use a Python package called ZAR, which allows you to compress large arrays in chunks and decompress the chunks you need to use, which is helpful. Because if more than 2 sensors are broken, I don't think I could even run the program without it. And so once we have that large array set up, we sum over all the Birkin sensor dimensions. For 2 Birkin sensors, it's 2, 1 for each Birkin sensor, and then this position. So next steps, I got to continue working on this project with my mentor Tina Peters. We're still working on integration, including the Poisson bivariate, because it looks like the more proper and probably quicker way to create the giant distribution. I haven't worked the working sensor data into the correlations which we need, and I would like to further optimize how we're using ZAR. And later add a lookup table to further speed up Python distribution calculations and write up proper documentation. Thank you for listening. Anyone has questions?
All right. Thank you, Zoe. Any questions for Zoe?
Just wanted to say that was some really impressive work. Thanks for showing it, taking the time.
Thank you.
And I see, I believe one of your mentors is connected. Tina, do you want to say a few words about Zoe's work?
Yeah, sure. I think Zoe did a really excellent job this summer. And I don't know if she was expecting this, but she, in addition to a lot of the work on the program she was writing, I think she learned more about particle physics and neutrinos than she had bargained for, and did an excellent job in this talk and like also over the summer of learning the context behind the problem she was solving as well. So well done, Zoe.
Thank you.
Great. Sounds like it was a positive experience. So that's what we like to hear. So
So I don't have a question, just a comment. That
sure. Go ahead, Jeff.
Very interesting seeing this work with Czar in a particle physics project. That's unusual, but Czar is a big deal elsewhere, like oceanography and such. So that was interesting to see.
Hi, I'm Abhishek, a research software engineer working for Princeton, and I have been mentoring Ivan here, who is joining us from Kiev Academic University. He's a biologist with a bachelor's, and he's working on his master's. And he really has no computing, at least when he joined, he didn't really have any computing background and much less anything about Python and Jupyter notebooks, very limited knowledge of these things. So he has patiently taught himself how to develop a Google Colab notebook for doing image segmentation of epithelial cell images and kind of exploring the parameter space of this tool that we are trying to use and get it to work for doing 3-dimensional segmentation. And I think he has done an excellent job, and there's a lot of more work to do that he's actually interested in continuing. So I'll hand it over to Ivan. Go ahead.
Thank you, Abhishek. Good day to everyone. I'm Ivan Prinko. Today I'll tell you about the project I'm glad to work on with my mentor, Dr. Abhishek Biswas. I'll share the results and future challenges as well. So the topic you see on the screen, the Python library is cellpose that does most of the job. So actually we need to put right parameters to take the right picture from the input image. Input image is a microscopic image of cells. So the easiest way is to just do 3D equals true, but it outputs kind of
your slides. We are not seeing your.
Oh,
I don't think you're changing your slides. Yeah.
You see the first slide?
Yeah, I see the first slide. I think you're talking about the second slide already, I think.
Yeah, sure. I don't.
I think you have to go into presentation mode, and that way you can.
Okay, I'll stop sharing. Okay, now I share entire screen.
Yep. There you go.
Do you see now?
Yep.
Okay. So input image in the right corner. And we need to get something more like in the middle, but with the simplest 3D processing, we get something a bit terrible, and we want something more likely on in the middle. To create something more complicated, something more better, we need to adjust it. And there are 4 parameters to put, and there are cell prop, flop, anisotropy, and stitch threshold. Actually, I'll explain later what each one of them means. So I like to group them into groups. First 2 are for cell recognition. They are like a 2-dimensional analysis to recognize particular cells, and the second group is for Z slices to kind of stitch the cells from one slice to another slice. So the cell pose should know which of the cells from the first slice is the same cell on the second slice. So that's the harder way, but it gives better outputs. So cell prop, as I mentioned, it like a 2-dimensional analysis, and with parameters from -6 to 0 and 6, it gives the results you see from the left to the right. I just show the range and its capabilities of this parameter. And yeah, all pixels with the value of cell prop about threshold kept from max, and yes, another 3 parameters are stayed the same for all 3 images. So we see just dynamic. Same here, 2D, and we see that the middle one is the best, kind of, because it has less noises like small particles that are on the 2 other images. So also fixed parameters, 3 others. Anisotropy is a bit more difficult, and as well as stitch threshold, because it's through the slices, we need to get an 3D 3D cells, 3D changes, but it will be solved soon, because as you see on the next slice, there are many kind of white blank cells that aren't actually figured out by cell pose. We'll need to fix it somehow soon, so it's the future challenge to get to know. But from the stitch threshold, you can see how it changes from 0.1 to 0.9 on the right side. So it somehow decreases in quality. But also it doesn't track, I mean. So in the second one, you see that some cells are actually stitched through the stack of images. But on the right side, you see that there are blank in the middle. So yeah, I take 3 images of 13 in general. So the first one, the 6th one, and the 13th one. So to get, we need to decide which parameters are the best ones. So to deal with it, we need to loop, for example, for firstly 2-dimensional parameters. There are cell recognition parameters, flow threshold, and cell prop threshold. We loop it, so in Python it's like double looped, and we get such table. These numbers are number of cells, or in Python, it's kind of amount of unique values. So it's kind of cells, but actually on the image, it can be also a blank cells that counts further. It's not stitched like through the stack, but they counts, and some large numbers are the outliers, kind of a lot of noise, these small cells that we aren't interested in. So we should take, in this particular example, a number around 500 and take it like take 500 and take, for example, 0.4 flow threshold parameter. It's not correct. And for example, 0 flow, or you see there is no change, we can take even -6 cell prop threshold. So, and with these parameters too, we see that 3D parameters aren't changed. They are default by the function of cell pose library, and we just add these parameters and also loop these 3D parameters, stitch and anisotropy, and get such interesting and probably false table. Also, we have a lot of a large number of cells that is incorrect. It can't be such a large number, so we need to take something less, and yeah, it will be for future challenges. So on the bottom you see the example that shows how stitch should work actually, and there is first image, first slice, 6 and 13th. But actually these blank spaces are also cells. They have some value in the cell pose library, and it should be stitched as well. Challenges. Actually, you see 3D image. It's like what was the purpose and what is the purpose and what will be handled soon. White cells is a future challenge, and you should address that. And 3D image, one of the way can it be, how can it be handled is with bipartite algorithm. It's kind of calculating the distances and between cells, and choose the right from one slice to another slice, and from the another to the third one, and so on. So I hope it will soon solve it with my mentor. So thank you for attention. Thank you for this opportunity to IRIS organizers, and so of course my mentor, Dr. Abhishek Biswas. Thank you to everyone.
Thank you, Ivan. Any questions? Okay. Thank you again for the good talk. Thank you everyone for your participation. Thank you to the fellows for the talks and the mentors for their work as well. We have another round of talks coming up in 2 weeks. So hope to see you all then. So thanks. Bye.
Thanks everyone. Bye.
Thanks. Bye.
Thanks. Bye-bye.
Bye.